Welcome back, students. In this lecture, we are going to start a new topic, and the topic is a perturbation method, which is again an approximation method. And in this method, we are trying uh, to learn the basic uh, 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 idea of perturbation method where what is exactly the perturbation method is, and how we can apply this perturbation method on different ODEs and PDEs, and um, at the end of a few lectures we will also try to compare both the solution of the perturbation as well as the domain decomposition method, the solution from the ADM, and we will decide at the end that which method is excellent in terms of approximation. So uh, let's start from chapter 7 of the book of Papanazzo, Viscous Fluid Flows, and from in that book they discuss in detail the perturbation method for fluid flows and generally for ODs. So here we have the topic which is called regular perturbations or a perturbation method. The regular perturbation method, first of all, we have an unknown function u of x in a single variable, or u of xt. If you are dealing with the PDEs, then this will be a function of more than one variable. But here we deal with the single variable unknown functions. So this u is depending on x, and this epsilon is some small number which is most probably belong in uh, 0 1 interval. You can say that this epsilon belong in 0 1 interval, or the value can be taken from this interval 0 and 1. It could be point 0.1, point 0.2, point 0.3, and point 0.5, or more smaller values from this interval. uh, Consider again the we are considering here a problem which if you can see here 7.28 in this book, this one exactly. This is an ODE, du by dx plus u is equal to 0, and this is the boundary condition for this ODE, and this is exactly the exact solution for this ODE. So we are trying to solve this problem using the perturbation method. So here uh, the first step in perturbation method is to uh, assume that the parameter epsilon is very small but not 0, uh, and we expand this unknown function in a series form. U of x epsilon is equal to u naught of x plus u1 of x epsilon plus u2 of x epsilon square plus the big O epsilon 3 and many more terms. So this is the series of this unknown function u, which is depending on x, has this series form, and this can be written summation uh, um, I from 0 to infinity ui into epsilon power, you can say epsilon power I, because it start from this one. The series will be like this one: u of x epsilon is equal to summation subscript value, I start from 0 to infinity. um, ui and depending on x epsilon power I. This is exactly the series for a Bowen function. So you can, if you expand this series when I is 0, so it will give you u naught epsilon power 0, and epsilon power 0 gives you 1 plus u1 epsilon power 1 plus u2 epsilon power square, and so many more terms. Where u naught u1 are unknown functions of x, and this equation 7.32 is called asymptotic expansion or perturbation of the solution in terms of the parameter epsilon. So this is exactly the asymptotic expansion or the series expansion of the unknown functions in terms of epsilon. So once we substitute this series in the above differential equations 3.7.28, and if we recollect and simplify all the similar terms of epsilon, powers of epsilon, we obtain this equation. Uh, if you revisit to that differential equations, in that differential equations we have du by dx. This term is involved, plus u, which is depending on x, is equal to 0. This is exactly the form. So we replace all these u's by this series. First we need to differentiate this expansion. So we need to find the du by dx. So once you differentiate this series, so it gives you du naught by dx plus du1 by dx plus du2 by dx into epsilon square, and so many more terms, and the expansion of u. So once we plug in all the values of du by dx plus u and rearrange all the powers of epsilon, we will have exactly this differential form, or this form for the above differential equations. Now from here, what we are doing, we are trying to collect the the powers of epsilon. So the equation must satisfy for any value of epsilon as epsilon goes to 0 or tends to 0. Therefore all the coefficient in this equation must vanish, which yields for epsilon 0. The this term has epsilon power 0, so it should be uh, this one, du naught by dx plus u naught is equal to 0. And similarly, the boundary condition must be expanded as according to the this series, and we can calculate epsilon power 1, which has this value. This value has epsilon power square. So these are the order differential equation for the above expansion. Now once, if we uh, solve these order solutions or order differential equations, then um, uh, we will be able to find the perturbation solution for the above differential equation. So the solution of this zeroth order epsilon has this value. This is exactly the solution of this differential equation, zeroth order differential equation. The first order differential equation has this solution, and the second order differential equation has this solutions. So once we substitute these u naught, u1, u2 in this equation, in this exactly in this perturbation expansion, asymptotic expansion, then we will have exactly this series. And this is now called the perturbation solution for the above differential equations. And if we put epsilon equal to 0, then it will almost give you exact solution, this one, which is the exact solution of the zeroth order. So this is exactly the perturbation solution for the above problem.